Okay, so this is the one we're going to be working through next. We've got this beam here, distributed load, and then it's got this 400-pound force that's applied. There's a bit of a twist in that the force is applied kind of on this arm that's hanging underneath. So we'll talk about how to deal with that as well. But first things first, let's figure out what the reactions are. I've got our free body diagram up here. Got cut off a little bit at the top. That's just me writing in the resultant of that 400 pound per inch distributed force. That'll be 480 pounds since it's spread over a 12-inch area. And we got this gap here. Then we got the arm coming down here, the 400 pounds, and our reactions. So first things first, which one's usually the easiest to do? Sum of the forces in the x direction is equal to 0. Therefore, Bx is 0. Cross that one off. Yay! Next up, I'm just going to take the moment about point A here. So we've got the moment caused by the resultant of the distributed load. So that'll be a negative moment since that's acting counterclockwise. Sorry, clockwise. So negative 480 pounds times 6 inches, because again, the resultant is going to be located halfway between the span there. We've got the 400 pounds times the 22 inches from here to here. Again, clockwise when taken about A, so it's a negative moment. And then we've got our reaction at B, so that'll be a positive moment when taken by A, because that one is presumably going to be pushing up. And then when we rearrange stuff, we can solve for By as 365 pounds. So yeah, it's a positive value that we solved for there, so we were right in our assumption that By is pushing upwards. Next up, we just take a sum of the forces in the y direction, and that'll give us our Ay minus 480 minus 400 plus 365. Solving for Ay by moving all the other stuff to the other side of the equation gives us 515 pounds. So we got our reactions. There's the question of how to deal with this overhang here. So the way to do that is basically to kind of replace this with an equivalent force moment couple system. So if we have this force coming, if we have the force coming down here, we realize that we can shift it back and forth along this little kind of section of the overhang here. And we can do so and have it be equivalent as long as we add a moment that would be equal to the amount of the moment that would be caused by this force relative to the spot that we're moving the other one to. So if we shift the 400 pound force here over to this spot here, then relative to here, this force here would have caused a 1600 pound inch moment in the clockwise direction. So, and then that's just 400 pounds times the 4 inches that shifted over. So we've got that. And then from there, we can shift the force moment couple, or sorry, the system upwards without impacting things because it is moving in the line of action of the force. So we don't need to add any additional movement, any additional moment to go from this point to this point. Shifting upwards like this doesn't matter. Then after that, we've got this section here that's hanging off there. We can just get rid of that because there's no forces there. Or at least no equivalent forces left. Unless, when we're analyzing how the bending moment and the shear acts across the beam. Obviously, we may also be worried about analyzing the load in those bars there too. And if that's the case, you'll be asked to do that. But kind of just redraw a free body diagram with that equivalent force moment couple system in place. So we got our 515 reaction. We got our our 365 reaction. Got our load, our point load. We got our moment applied there. We've also got our distributed load. So I'm keeping this one in the distributed load because we're going to be using this to draw our shear diagram. So essentially, basically, just start from one end and work your way to the other. So essentially, you got to keep in mind the rules. If we are when we're moving from left to right on the graph, if we have a force that is applied upwards on the beam, that causes a jump up in the internal shear load at that point. And then a distributed load can act either upwards or downwards, although majority of them are going to be acting downwards. There's some sort of a gravitational force. They're representing some sort of mass distributed over the space. So we jump up to 515 at the start based upon that point load, and then we've got this distributed force here, and that pushes us down, so that gradually decreases the shear until you get to the point where that stops. And the slope of this line is equal to the magnitude of that shear of that distributed load. So we're going from 515 pounds, and we're dropping by an amount that is equal to the 40 pounds per inch times the 12 inches it's distributed over. So the total amount that is dropped over this section is going to be equal to the amount of the resultant of that load. From here to here is going to be equal to the 480 that we calculated earlier. So we're dropping from 515, subtracting 480, that gets us to 35 pounds. So this little section in here has a constant 35 pound positive shear load, internal load. And then we get to that point there, and I would like to point out that the bending moments don't affect the shear. It's the other way. It's the other way around. The shear affects the bending moment, but the bending moments themselves don't affect the localized shear. Although applying a bending moment to an object can affect the shear in as much as it will change what the reactions are. But beyond that, when we're doing our shear diagram, we're only worried about the actual forces involved. We're not worried about the moments. So the only thing that happens on this diagram here is that it drops down by the amount of this point load. So we got a 400 pound point load here, and we see ourselves dropping down 400 pounds, so 35 minus 400 brings us down to negative 365 pounds. Now that amount stays constant over this length until we get to this point here, and then we get to this force right here. So that causes us to jump up, and we're jumping up by an amount equal to 365 pounds, which, hey, thankfully brings us back to 0, which is exactly where we expected to be ending when we finished up our diagram. If you ended up getting to a point other than 0, well, there's something wrong with your diagram, and you should go ahead and revisit that. So next up, we are going to be worried about what happens to our moment diagram. So we know that the endpoints are going to be 0 because there aren't any reactions, because they're both pinned at the end. There's a pin here, there's a pin here, so there's nothing there that would be causing like a point moment at that point. The internal load, the internal moment kind of develops over time with shear, unless you have some sort of reaction at the end where you have a moment couple applied to the end of the beam, such as what we saw with this previous example. Any fixed connection at the end will cause a moment, will cause a non-zero moment at the end of the beam, but doesn't happen on this end because that's a free end, and it doesn't happen here or here because those are both pinned connections. They're specifically designed to allow it to rotate. So because it's allowed to rotate, there's nothing there to resist rotation, and so there's nothing there to generate a reaction moment. So we know that it's 0 here, and we know it's 0 here, and we can just go ahead and kind of start from either of those points and work our way towards towards the other end. So when I was looking at this, just looking at this, it seems to me like the easiest way to start would be to start from this end and then kind of draw this straight line, because starting with a straight line helps. So we're starting from here and kind of working our way backwards to here. So we know that the magnitude of the drop from here to here is equal to the area of this section here. So that'll be the 365 pounds times the distance from there to there, which is going to be our 10 inches plus our 4 inches, so 14 inches. So 365 times 14 inches gives us a magnitude of the change of 5,110, and again from this point to this point it's a drop because this shear here is negative. So we can just and we know the endpoint here is 0, so we know that kind of when it starts dropping here, that means that value there is 5110 pound-inches. Then, like I said, we're worried what happens on the shear diagram when it comes to the moment diagram, but we're also worried about our point loads. Like I said, the point loads don't show up on the shear diagram, but you definitely need to take them into account. So again, when going from left to right, a negative moment is going to cause a increase in the moment. When we're going from if we're working from right to left, the opposite happens. So if we're starting from the right and we have a negative moment here, then it decreases as we hit that point. So at that point, the moment drops down, and it drops down by 1,600 pound-inches. So that'll bring us to 3510 pound-inches at this point. So then we've got this linear section right here. So again, we know that that section there is linear because the shear load over this area is constant. It's a constant 35 pounds. So we know that the slope from here to here is going to be a constant 35 pounds. So if we're starting from this end, we can take our 3510 and subtract from that 35 pounds times 6 inches. Again, this is a 6-inch span, and that gets us down to 3,300 pound-inches. And then at this point, it stops being linear, although I'm going to zoom in a bit here. So it stops being linear at this point, but at that instant the slope is still the same, and then the slope changes and then gradually increases, going from right to left. If we're looking at it from left to right, you got a slope that starts off at its maximum and gradually decreases until it gets to that point. Maximum slope, minimum slope. So it drops off quite a bit, and this will be a quadratic kind of a equation between here and here. So that's that curve there. So again, the magnitude of the drop-off between here and here is going to be equal to the area under this curve. So if we want to calculate that, we need to break this up. So we need to break it up into its two components. We've got this section here, this thin skinny rectangle, and we've got this triangle here. So again, the height of that triangle is the 480. That was the resultant of that force there. Base of the triangle, base of both the rectangle and the triangle is 12 inches. So we can calculate the total change in the moment. That's going to be 480 times 12 inches divided by 2, because again, triangle, not rectangle, plus the rectangular section, 35 times 12. So plugging that into our calculator there, 480 times 12 divided by 2 is 2,880, plus an additional 35 times 12 is 3,300 pound-inches. Hey, guess what? That's exactly the amount we expected to get. So we started at 0, we increase a bit more, we jump up, we drop down, we get back to 0. So as long as you start from one end and work your way to the other, applying the change in the gradual changes in the moment are going to be based upon the slope being equal to your shear, and then the abrupt changes are just going to be based upon what sort of point loads you're adding. As long as you get back to what you expect to get back to, then you're good to go. So again, if you have say a situation where you have you have, say, a cantilever beam that's fixed at one end. You can expect to, and then say, a load of some sort here. What you can expect to happen is, in order to counteract the moment from this from this force, the reaction is going to cause a counterclockwise moment, which means that the internal moment diagram is going to start off at some negative value. Again, we're moving from left to right, adding a counterclockwise or a positive moment actually drops us down. And then across this span, that section would be linear because the shear would be constant. So start off in some instances. Essentially, what we're saying here is you're still kind of starting at zero. You start at zero, but you get an instantaneous. Here, let's. We get an. Oh, not letting me change colors. Let me change colors. There we go. We get an instantaneous and abrupt decrease in the internal shear. So we start from here, and then we go down instantaneously, and then we work our way back to zero. So start at zero, end at zero. Same thing works to the shear. Essentially, we're kind of starting at zero, but we get an instantaneous and abrupt. Come on, let me change the colors. Starting at zero, instantaneous and abrupt increase, gradual drop, constant, instantaneous and abrupt decrease, constant, instantaneous and abrupt increase back to zero. So, same idea works. And that is about that for how we go about to construct our shear diagrams and our bending moment diagrams. Now, the alternate way of doing this would be to essentially take a lot of sections and kind of analyze how the shear and analyze what the shear and what the moment would be across each of those sections. And for some, the problem is that sometimes that can be difficult for students to kind of parse, especially when you get stuff like here. Like someone might take, I've often seen come on, I want eraser. No. Sorry about the interruption. So oftentimes, especially if you're going by sections, you might see students. I've seen students try to do that by, say, taking a slice right here, kind of say immediately to the left of, immediately to the right of where the moment is applied, and then they think, okay, well, I took a section right there, so that's what the moment is at that point, and then they don't take another section immediately to the left of that, so they don't capture that drop if they're relying upon just taking sections at various points. So I really do think that kind of using the diagram method of tracking how your moments and your shear changes is probably the ideal way to go for the most part.